Okay, and welcome again to the second part of the bunch of chapters, which deals with all the phases basically of matter, namely solids. We did that for the most part, and we also did liquids for most part too. And we did not actually do gases, which is going to be finished today. And as I said before, before recording, we're going to actually touch upon the plasma state, a little bit of it, not too much. And that's basically the end of this stuff that is for exam for the midterm. The review is on Canvas. All you're supposed to do in order to proceed is mark done that you actually did the review. I know it's a lot of problems there that you need to go through, but please do that, okay, one by one, systematically. You have to have an understanding of how those solutions are. If you have difficulty with one or a bunch of them, please let me know. If it's something that is probably a quick answer, I'll give you that. If not, what probably we should do is we'll go on a session together and record it and post it back on Canvas for everybody to benefit from. So that's basically in a nutshell what the review is. The exam is actually on Tuesday of next week, a week from today, at the same time when we're meeting right now at 4 o'clock. It's going to be on Canvas. The exam is actually timed, although it's open from 4 o'clock until, is it 10 p.m., I think? Let me double check to make sure I give you the correct answer. The
I
correct
think it was
information.
11, but I
Probably
think
11. I just want to make sure. Hold on. Okay, the midterm. Actually, I'm going to open it right now. Oh man, I probably should not have opened it that way because it did not give me the details of it. Let me right click and make it as if I'm editing it. Edit. That's not working either. Sorry, let me get the information because I really don't want it to be confused, at least for me. If I said it's 11, it's 11. If it's 10, it's 10. But we have to make sure it is what it is. So we can't really change it in here. Okay, so I think from here, can we edit more options? Yeah, the exam is open until 11, okay, from 4 p.m. until 11 p.m. And it's timed exam, as I said. The number of attempts is 1, okay? And it's timed in a sense that you're only allowed to basically, I think for an hour and 25 minutes, meaning that you should really allow yourself for plenty of time to review your questions before you're actually making the submission. Now, I will open a discussion session with the first question that pops up on it, if in case it's worth making changes on the exam. Let's say, for example, there's a problem with a specific problem. I probably need to fix this or that, or it doesn't make sense to you or something like that. So you go in and you have to be specific, okay? You can't just tell me problem 1 has a problem with a picture, or problem 3, the picture is not clear or is not there, or it's referring to a picture that doesn't exist or something like that. Because I will open your exam, your exact session of the exam, and I probably will see what you're talking about, but be more thorough because the exams for you, problem 3 is probably problem 7 for somebody else who doesn't have it at all. For somebody else doesn't. So the next person probably is looking, what is he talking about? And problem 3 has a problem. There is no picture in here. Do you understand what I'm saying in here? So you have to be clear in your question so that the answer will be as clear as possible so that they can go quickly through it and fix what needs to be fixed and make the announcement stating if you're doing this problem, here is the thing with it. So somebody else might look at it and say, oh, that's not me. I'm not doing that problem because it's not part of the questions that I have in the bunch that I have in here. I will not answer any kind of a question that come after 10:30 p.m. First of all, I will be sleeping. Second, it doesn't matter by then that if I make any kind of corrections, it's too late for anybody to adjust. Probably some of you have already submitted and they think that it's all done and probably sleeping. So after that time, I will not be responding, basically. That's one thing. The other thing also is that please do subscribe to the discussion forum, okay, so that you will receive notifications from Canvas that there is a posting. Probably you would want to go and look at it. So that's what I want to say in terms of the exam. So it's timed, an hour and 25 minutes. Once you start it, you have to finish it, okay? Submit your exam, and then you can go and sleep or do whatever you want to. You're working, for example, you get off work until like 5 p.m. or 6 p.m. Then don't start the exam until you actually get off work, and then start it and finish it before the deadline. So basically, that's in a nutshell what the exam is. It's taking into account the people who work during daytime. And if you happen to be, for example, you have a shift at night that starts very late, then you are going to start it early and be done with it, and it's all over. Okay, so that's basically in terms of the midterm. And the review is actually on Canvas, so hopefully every one of you guys will go through those questions in the review. I think there are 27 of them. So if you understand them, that's basically the promise I'm giving you. If you understand how those things work, if you know how these things, how to answer them, variations of them, changes to them, so you should be 100% ready for the exam. Once the exam opens, you're going to log into Canvas and start taking the exam, okay? Once you do that, you're going to be faced with basically the problems. And at the end, there is an additional question, the 13th question. There are 12 questions, by the way, in the exam, in the term. The 13th question is actually, it's for you to upload your work, okay? Because if your answer, for example, is wrong, and I don't have your work, there is no way for me to guess basically if you did the steps correctly leading to the answer. So it's a good idea to keep your at least a clean version of your work. There will be probably scratch paper on one side and maybe clean version of your work while you're working on it, and then submit it toward the end, basically include it as part of an upload. Here is page 1, here's page 2, page 3, and then upload those things so that to give me a chance, or to give yourself actually a chance for partial credit, okay? So that's in terms of how the exam is supposed to be working. I think it's going to be clearer probably by Thursday when we meet again as far as what needs to happen for this one. But we really need to finish the content first. So if you don't have any questions right away, I'm going to jump into the PowerPoint. And when we left off last time, I believe we got into a lot of these things in here in terms of these questions and buoyancy and things like that. Archimedes principle is really the next topic in here. And basically it says that denser fluids will exert a greater buoyant force on a body than less than dense fluids. That's another thing in terms of Archimedes principle. This is a continuation of a discussion that we've been having actually on it. In a sense that, for example, salty water. Yeah, I know, but the other questions, Kyle, they were just questions, basically. I didn't think that they're worth, honestly. I want to get to the ideas, and then we will finish the topic and continue on, okay? So I think I'm aware of that too, honestly. I think those are a bunch of questions and answers. So anyway, salty water is more dense. So in this case, because of the higher density, the object does not need to displace as much fluid as it would for a less dense fluid, okay? I think that's part of the lab for the people who are taking physics 11 too, when they change the density of the fluid and they see that actually that works too, okay? So the more denser fluid, they will experience the same buoyant force though, because at the end, the buoyant force is going to be basic, especially if they are submerged, is going to be the volume displaced, and the volume displaced is that of their own liquids. I'm sorry, did I say that? Oh, no. When they're afloat, yes. But when they're submerged, no, because the weight of the displaced fluid in this case is going to be different because it's a newer density, the volumes are the same. Okay. And it applies too in air too. So this is how balloons work too. They displace the volume of the balloon, okay? Hence, they start to rise because the pressure below is higher than the pressure above, and they will have a liftoff in this case. If you know the difference in height, for example, in here, you can calculate the difference in the difference in pressure, I'm sorry. Once you have the difference in pressure, then you will find how much this whole thing weighs, including the people on it and everybody else. Then from there, you have the weight of the object and the difference in these two pressures, times the area in this case in here, that is going to give you a lift force, okay? The lift force, which is a buoyant force. So in this case, if it is more than this entire weight, then in this case you can continue to rise, okay? You can continue to climb because the buoyant force is greater. So that's how they used to do it. I mean, at some point they would want to rise higher. So what they do, they start throwing other things just to climb higher and higher, okay? Or probably start feeding more and more in here hot air so that the balloon expands and gains more and more space in here in this case. Or if you want to, you start escaping the air from the other side if you want to descend. So that there is less and less buoyant force, which brings you down. So as you sit in class, of course, we're not sitting in class, we're sitting at home, is the buoyant force existing on, is there a buoyant force acting on you? Of course, yes. And that's really due to the displacement. You're displacing the air, okay? That's basically the buoyant force. So there is a buoyant force, but your weight must be greater than that of the buoyant force. Otherwise, you start floating. This was also part of an experiment that we discussed in Physics 11. Whether an object will float or sink depends, first of all, on the volume displaced. If it displaces more, it displaces a volume large enough so that the weight of the volume of the water displaced is equal to or greater than that of the object, then the object will float. And that was part of the second part of the lab where you guys build the actual paper boats and make sure that they float. And as I said before, in a physical lab where we meet face to face, we could have done that and embellish it with competition where you guys actually start putting paper clips and see which one sinks. As a matter of fact, for this specific boats, the ones that I gave you, paper clips are not enough. You really need weights there. You need you start with probably 50-gram weights, and then you go your way up to see for it to sink, because they are solid actually. They don't sink easily. So, and again, if now if the object is already submerged underwater, okay, there are three possibilities. If its density is less than that of the fluid, then it's going to float. If its density is greater than that of the fluid, then it's going to sink. If its density is the same as that of the fluid, they have the same density, where you put it, it's going to stay. Underwater, of course. If you put it anywhere in the level of the water, it's going to stay. It's not going to sink or float. So that's in a nutshell what this whole idea is. An object more dense than a fluid in which it is immersed, it's already immersed in it, will sink. An object less dense than the fluid in which it is immersed will float. An object having a density equal to that of the fluid in which it is immersed will neither sink or float. So we're going to stay where you put it in, where it's immersed. Two solid blocks of identical size, and the key word in the whole thing is identical size. Everything else, ignore it at this point, okay? You don't even have to bother with the rest. What kind of objects are they, okay? If they have identical sizes, then one block is lead and the other aluminum. We don't care about that, okay? They could be whatever you want to make them out of. But since they have the same size, upon which the buoyant force is greater, it doesn't matter what they are made up of, because both of them will displace the same amount of liquid, since they have the same size, the same basically volume. So both of them will displace the same amount of volume. Therefore, they have the same on both blocks. So the buoyant force is neither greater on lead nor that of aluminum. Granted that lead is far more denser than aluminum, who cares? At that point, lead probably will sink further, much faster than aluminum, because it has greater weight. So it's the difference between it and the buoyant force is much greater than that of aluminum. But that's not the question. The question is, which one has the greater buoyant force? Neither. They have the same. The buoyant force is the same, because what matters in this case is this key word in here. Okay. Which brings me to YouTube. If you probably haven't heard of YouTube yet, this is it, okay? This is probably how physics has, I mean, it was known YouTube way before to physics than it was known to the popular culture, basically, from now for what you guys do when you go home and watch stuff and things like that. Anyway, this has a lot of applications. Okay, one of its applications actually is the way to actually measure densities, relative densities of different fluids. You can use a YouTube for it. Okay. Also, one of its applications is the hydraulic press, which we're going to talk about it right now. And then the whole thing relies on Pascal's basically principle, which basically states that if there is a pressure, if you exert pressure on one side of the fluid, that pressure is going to transfer itself throughout the entire fluid. So the same pressure basically will be exerted on the other side. You push with, let's say, for example, 100 pascals on one side, you're going to end up with another 100 pascals on the other side. Pascal is famous for a lot of things. I mean, he was a scientist, mathematician, philosopher, and a theologian. If you did not hear about his wager, he's famous with that famous wager, basically, that about the existence of God. That basically, anybody heard of his wager? Nope. It's a good topic to look at. Okay. It's philosophy and it's religion. Of course, he was a theologian. He was pro-God too. So he made an argument for it using basically the concepts of God from the church. And until now, it's a debatable issue, okay? But the point in here is that he was actually a mathematician too, and he was a philosopher, and he did a lot of work actually in this field also. That's why the unit of pressure is named after him too, okay? The unit of pressure is named after him. I mean, the wager is actually in a, I think it's a book entitled Pensée, which is a French word for thinking, I think, or what is it? Yeah. There is an accent over the first E. Anyway, so that's his principle, okay? That the pressure is distributed uniformly throughout the entire fluid. So if you exert pressure on one side, so which gives you an idea now that you can use it actually to lift objects. You can lift an elephant if you like, okay? And all you need is basically with your hand, okay? So if this is an elephant, 500 kilogram elephant, elephants weigh a lot more than that. But if this is a 500 kilogram, for example, tiger, you can still lift it easily. All you have to do is push with the 10 kilogram in here. Since the pressure of a 10 kilogram over this area, this tiny area, is the same pressure times the other, which is the force divided by the area, then you can still do it. So mathematically, since the pressure is force over area, so the force in here is of that of a 10 kilogram, which is 10 kilogram times G, which is 10. So the pressure on one side is, oh man, 10 kilogram times the force of gravity, times the gravity basically constant, which is 9.8 meter per second, divided by this area, which is a small area, okay? My pen today is working very slow. Is equal to 500 times the same G, divided by the big area now. And this area, I'm going to call it A prime because it's much bigger than the first one. Of course, the G cancels from both sides, so it's irrelevant, okay? I'm trying to lift a 500 kilogram elephant. I mean, no, tigers are less than that. It doesn't matter, 500 kilogram something, super heavy that I'm not able to lift with my bare hand, with one hand, that is. Because 10 kilogram, I can still lift it with, it's 20 pounds. I can just lift it with my hand. So the 10 cancels one of the zeros. So all I need to do is actually have this area 50 times the other area. So this area in here has to be 50 times the other area. And if I take the square root of 50, which is about 7, so if this length is, let's say, for example, 20 centimeters. This one is 7 times 20 centimeter, 1.4 meters. Okay, so that's it. I can push on a 10 centimeter with the equivalent of 20 pounds. I can lift 1,000 pounds on the other side. Okay, very simply, using this principle in here. Because the pressure is the same using Pascal's principle. Okay, so this is the principle behind the hydraulic press. So, but the trouble with this whole situation is I have to push very far away. Let's say, for example, a meter down for this one to rise 1/50th of a meter, which is 2 centimeters. Okay, so because the work at the end should be the same, I cannot create energy out of nothing. So if I need to lift this one 2 centimeters, I have to dispense of a work that must be equal at best to the work in here. Since I can only afford 100 newtons in here, in lifting 5,000 newtons in here, so the work in here would require a long distance so that it's equal to the same work of the other force. Again, remember, work is force times distance or displacement. So since the force in here is a lot less and the force in here is a lot higher, then the distance in here must be a lot higher the distance in here is a lot less to make up for the difference, so that I cannot create work out of nothing. That would violate one of the principles of the next branch of science that we'll be discovering starting from Thursday, namely the science of heat and thermal heat and thermodynamics, it's called. So again, now using the same principle, we can lift cars actually. The thing with it in here, it looks kind of odd a little bit, the picture. And in that the piston in here seems to have a smaller area than this piston, than this tank in here, this reservoir. But don't forget, what I'm providing in here is actually a pressure. The compressor in here, all it's doing is providing a pressure. And the pressure spreads throughout the entire liquid the same. In doing so, it's going to press on this gas in here and lifts the car, okay? And that's basically what you see in the mechanical shops. In mechanics shop, actually, they have something like this one. You come in, they push the button, and the whole thing starts to rise. And using actually hydraulic system to do that, okay? And at some point, you will hear the compressor go on and making a lot of noise, trying to build the pressure there, so that the next time when you use it, it has enough pressure in it. So that has a lot of applications. One of these applications is actually in here too. I mean, lifting weights and doing all kinds of things. So hydraulics are used everywhere, whether in brake systems for cars, whether to transmit pressure again. You will have an old lady, okay, I'm old too, so. Stopping a truck, huge truck, okay, going at 50 miles per hour. All she has to do is push the brakes on with her feet, exerting a pressure basically right there on the pedal. What she does in there with her feet is basically push the pedal. The pedal will transmit that pressure, basically the force she exerts on the unit area, because then it's coming through that cylinder, and that pressure is transmitted all the way to the brake system through using fluids, actually brake fluid, to the brake system on the truck, and brings the truck to a standstill, brings to stop it. So you don't need to be Superman to stop a truck. All you need is just enough pressure, and you don't have to have a lot of pressure, using basically Pascal's principle. So it's used heavily in a lot of things. So one of them is the braking system for big trucks, especially, and buses and things like that. I mean, cars, they probably use, they don't require a lot of hydraulics in them, and some of them do too. So, okay. So here one of the things. So which one is not possible in this whole thing? And you have to be very careful with questions of multiple choice, okay? There will be no quizzes this week. There will be no homework this week. It's basically a review only for the exam, okay? So the only thing that is due this week is the chat sessions after the, the discussion sessions after after the classes, basically. That's the only thing, okay, the participation stuff. So Which one is not true? Output piston to move further than the input piston. You can reverse them, so you can do depending on what you're doing. Because in this case, you really want, let's go back in here, the car to rise higher so that the mechanics can go underneath. You don't want it to rise 2 centimeters, that's too low, okay? You want it to go much higher than that. You want it to go very high so that he can go underneath. So it's probably going to be at least 2 meters so that a person standing can work on it. And that's why the cross section in here is a lot bigger so that this can move further than this one in here that needs to move just a little, because this compressor is, like I said, providing pressure, okay? So in this situation, that's possible. The output piston speed to exceed the input piston speed, again, that has to do with the power that is delivered, force times time and all of that. The energy output, the force output to exceed the force input, that's basically part of it too. That's what you want it to. You want to lift the bigger force on one side. So you want the forces. That's one of the things with it. This is actually a kind of a simple machine. This is a simple machine. Basically, the output force and the input force, the so-called effort versus load. So you could end up with a higher load. A 500 kilogram can be lifted with the equivalent of a 10 kilogram force. Okay. So A, B, and C are all correct. So the only choice I guess we have is the energy output to exceed the energy input. If that's true, then you have discovered perpetual motion, which was one of the things that people thought possible initially until the onset of thermodynamics, which said this is a violation of one of the basic laws of nature. You cannot have energy for free. You cannot have energy out of nothing, because if your input is this much, and if your output is this much, then theoretically, this input and the output can cancel up to this one, and you will have energy for free this much. And this is not possible. This is a violation of one of the basic laws. So that's D, actually. And I already mentioned that to the fact that if one of them moves slightly, the other one will move accordingly so that the energy at best is the same. Of course, the output is always less than the input because some of the energy is wasted actually too. So you cannot just have more energy. It's not that you can have more energy. In practice, you cannot even have the input energy. You will have less than that. Okay. So the correct answer is the wrong answer because you're looking for something that is not correct. And the thing that is not correct is D, which is the correct answer. So it sounds kind of a contradictory statement, but that's exactly how some of these questions are structured. So if you answer A, meaning that this is true, yeah, it is true, I agree with you. If you answer B, because you think that this is true, and it is true, you're right. And if you answer C, and you think it is true, and you're right. But that's not what we're looking for in this question. We're looking for the wrong answer. And the wrong answer is the correct choice in this case. Okay. The surface tension is one of the key things in here. And you will hear a lot of people, I know it was one of the early discussions that we have had in the beginning, is the earth flat, and they use the argument that, what is it, water seeks its lowest point, or some nonsense ideas in there. And they forget about the surface tension, and you can do an experiment, a very easy experiment, where you can look at the side of the glass, and you will see that the glass, this water there is curved. Because again, it's trying to attach itself to the walls. When there is no walls and when there is water dropping by itself, it comes always in a circular, a spherical shape. And if you have a fast enough camera to capture it, you will see that. Okay, you will see that that's actually spherical shape. And again, because the surface tension, because the water on the edge, I mean at least on the surface, I mean, the molecules of the water everywhere inside the fluid, they're connecting to one another and interacting with one another, and they don't have a problem. When it comes to the surface, the water molecules in this case, they can connect from the bottom, but they don't have anything else to connect from the top. So they try to basically build that bridge, and that creates a force on the surface. Okay, that's how you see some of those lightweight animals basically work on the surface of the water. And if Jesus actually walked on water, that's probably what he used too. He probably must have understood the subject. Okay. I'm not saying he did or he did not. That's not my argument. The point is surface tension in here. So again, the shape of the droplets. Again, I talked about those. And this is exactly my point in here. Water molecules will interact with all kinds of molecules in the bulk of the water, but when it comes to it in this side, they will have a net force trying to stretch the fluid one way or the other. Okay, and that is the essence of the surface tension. Capillarity is another property of fluids again, and that is unique to fluids, and that is because the water tries to adhere itself to the sides of the tubes that you put them in. And the experiment has shown that first of all, it depends on the viscosity of the fluid itself, how viscous it is, and second, it depends also on how thin the tubes you're going to place it in. It will be a fun experiment if we meet to do this one in here. The thinner it is, the higher the fluid is going to rise in here. Okay, so let's get into the next topic. How are we doing on time? We still have about an hour or so to discuss, half an hour, I'm sorry, to discuss the little over half an hour to discuss gases. Okay, again, gases are in a sense fluids too. Actually, they are fluids. They are not liquids. They have different properties in the sense that the biggest difference is they occupy the volume you give them in, you put them in, okay? So that's the biggest difference, whereas the others, they don't, okay? The pressure of a gas, again, is, at least the atmospheric pressure is caused by the weight of the air above where the point we're trying to measure it. Again, similar to the pressure in a gas, this is also similar to that, but that's measured from the surface of the water below. This one is measured from the upper atmosphere, which really doesn't have a limit. So you're trying to go and find where the atmosphere ends, and you will find always molecules of air no matter how far you go. But at some point, you're going to read the pressure and you say, okay, there is no pressure at this point. There is practically zero pressure. From that point below, the weight of that fluid, the weight of that gas is the atmospheric pressure. Experience has shown that if I take 1 square meter, 1 square meter is slightly about the size of this desk, okay? Which is, if you step outside, if you stand up and you step and you open basically a large step from your feet, between your feet, that is about 1 meter. And if you do two of those, one of them perpendicular on the other, that is 1 square meter. The weight that is on that square meter is 101,000 newtons. That is about, it's exactly 101,300 newtons. So in Pascal, since that's the whole thing is 1 square meter, that is basically how much pressure it is. On your shoulders right now, which is a lot less than a square meter, it's actually slightly less than that number, okay? That's how much you're carrying with you all the time. So if you think you cannot handle a lot of weight, you are actually carrying that much weight right now as we speak. So that is the pressure. So what it is, it's weight of a column of air on a square meter. And it's a rounded number that is important for you to remember, 101,000. So the K in here stands for kilo Pascal. So the unit for the pressure is a Pascal. Some other times they give it the 1 atmosphere, 1 ATM. So 1 ATM is 101,000 Pascal. So if you see in the notations, 1 ATM, it stands, or 1 atmosphere, it stands for 101 Pascal, kilopascal. Sometimes they give it also the bar, okay? So that's another unit for the pressure. But the thing to remember is that Pascal is the SI unit. So if everything was in kilogram, meter, and second, and an ampere, then the pressure will come out straight out in Pascal. So it's a Newton per meter squared. And all of those in Pascal. So all of these units are just in terms of practical day-to-day pressures. So this is the equivalent to the weight, to the depth of 10.3 basically meters of water, basically. Okay, so that's how much you can think about it, because the density of water is about 1,000 kilograms per square meter. The density of water is a lot less, is 1.29 kilogram per cubic meter. Okay, so 1,000 times less. So that's basically how much the difference between them, which is important in here. There is no way for you to basically using the pressure, the atmospheric pressure only, to pull the water from depths deeper than 10.3 meters. So mechanical pumps that don't depend on atmospheric, of course they can go below the 10.3, but if you're using the air, the atmosphere, that is the maximum limit that you can do. So if you're going to have to, for example, using a straw to use it for example, for drinking fluid, if the container is longer than 10.3 meters, you can try as hard as you can, standing, of course, on top of it. Because if you have it straight out, then you can, because the level is still not 10.3. But if you're standing on it trying to basically drink, you cannot do it if it's more than 10.3 meters, or 32 feet, that is. And that's the point in here. The maximum height to which water can be drunk through a straw is 10.3 meters. Okay, not 76 centimeters. 76 centimeters is less than a meter. Less than a meter. 76 centimeters. No, it's actually more than that. I'm sorry. It's about 3/4 of a meter. Okay, so you can have a bottle that long, and you can basically use straws to drink from it. There is no problem with that, even if the water is right at the bottom. Okay. Which brings me to the barometer, which is how to measure the pressure. If you use mercury, for example, the atmosphere on one side has 101,000 Pascal pushing on the liquid. Okay. Well, the liquid in this case, the mercury, which is in liquid form at room temperature, is also has this much weight, 76 centimeters or 760 millimeters, the same thing, of weight, but the density of the fluid in this case of the mercury is much higher than that of the even water, so it's much more denser than it. So it doesn't require the entire atmosphere. So in this case, that's all there is to it. So if you want to create vacuum, because there is no way you can create vacuum with any pump, even if you go outside of the Earth, that is impossible. So this is a machine that does that, because actually that point in there, it's pure nothing. There is absolutely nothing in there. Vacuum as it can ever be. Okay, no air in there. So when the volume of the barometer, when the level of the barometer drops like this one, that is basically how much. And now this thing is actually scaled. Okay. And I can check the pressure outside, put it outside, and check the pressure of the atmosphere. Is it going higher? Okay. So if the pressure in here is going higher, the level of the fluid in here need to rise to compensate for it. Okay. If the pressure in here is less, the fluid drops down to compensate for that one too. So when you hear the weatherman talks about the pressure rising or dropping, that is what they're talking about. It when they say it's this many millibars or this millimeter, basically mercury, or then they say the mercury rising or the mercury. That's what they're referring to, is basically the measurement. And usually it's in relative. When the weatherman talks about it, it's in relative to the atmospheric pressure. So whatever number they give you is basically relative to atmospheric pressure. So the big atmosphere of the atmosphere is 101,000 Pascal. That's a huge number. So when the pressure drops up and down, that impacts the weather drastically. As a matter of fact, the voice that you're hearing right now coming from your microphone or whatever, your speaker, I'm sorry, is it's creating a pressure in the atmosphere in the room where you are, and that pressure is hitting your ear, and that's how you detect actually the sound to begin with. But that pressure is a minute change in the entire pressure that is produced by the atmosphere. Yet we hear it, okay? Because our ears develop sensitivity to that changes in the atmospheric pressure. That's how we hear, okay? That's how we hear sounds to begin with, through that pressure. So that's the concept of pressure. So the barometer is an important tool that we have to use in order for us to basically measure pressure. Okay, question. Why don't we use water? Why do we have to use mercury? Because if we're going to use water, it has to be at least 10.3, or it has to be more than 10.3 meters high in order for us to produce the same pressure. So if this were water, okay, I have to have this height to be more than 10.3 meters, about 33 feet high. Can you imagine yourself walking with a 33 feet high barometer to measure the pressure? It's too much, okay? So that's why we don't use it. So water cannot be used. It does not exert pressure. That's not correct. There is pressure from water. Water cannot be used because it sticks to the glass. That's not true. That's not the reason why. Water can be used, but the barometer will be too tall. That is the correct answer. It's going to be too tall. So you can use it, but it's not practical. Okay, this is another kind of barometer. Okay, that uses actually the difference in pressure and translate that difference in motion in actually in a rotational motion. Okay, and then can calibrate it in such a way to read the readings in there. Now, Boyle and other basically scientists have worked a lot on the properties of gases, and one of them is Boyle's law, and Boyle's law says basically for the same fluid at the same temperature, the product of P and V are constant. So this product of these two numbers is constant. That means if the pressure increases, the volume decreases, and vice versa, okay? Meaning that the pressure is inversely proportional to the volume. So PV is a constant. So the product of the pressure and the volume is constant. So if the pressure, for example, doubles, the volume shrinks by a factor of half. Now in this case, the volume is half. There's too much pressure now. So when you take a piston and you move it, and you look at the needle in here for the pressure, the gauge in here, it's going to read much, much higher, which brings me to a point in here. What this gauge is reading is the difference between it and the atmospheric pressure. So that's what the gauge reading is, okay? So now at normal, probably this volume, you're going to see a reading. You shrink the volume by a factor of 2. It's half its own original volume. Now the pressure is going to double. So there's too much pressure in the fluid now, okay? And you can try it with a balloon, for example. If you squeeze it, you're going to see more pressure that it could pop the balloon. And that's the pressure that does that. So again, PV is constant, meaning that if pressure increases, the volume will decrease and vice versa. So basically that's the entire expression here. So since the original state, for example, has a P which is very high and a V which is very small, and now you change the pressure to a small number, V has to increase accordingly or vice versa, okay? As a matter of fact, that is a more governing law than this one, okay? There is the ideal gas law that actually tells more, because this law only talks about pressure and volume, and the ideal gas law, which is a combination of several people's work, okay? I think Charles is one of them and other people. So PV is equal to, and you will see this one in chemistry. So if you ever taken chemistry or you have heard of this law, or if you did not, it's one of the basic laws that is actually worth knowing. N is the number of moles. R, which is just a constant, like the number 2, it's actually 8.13, okay? Times T, and T in here is the temperature. The only problem with the temperature, it's not measured in Fahrenheit, it's not measured in centigrade, it's measured in the units, which is Kelvin, and we will see this law again down the road when we play with the gases with the ideal gas law. So this law of Boyle is just a special case of this big law, okay? So we're going to talk about this one down the road. So I'm just giving you a heads up in here because this is just a special case of that big one. So when the number of moles is the same, provided that this is the same number of moles, meaning there is no leaking gas and there is no influx of gas, when the temperature is actually the same, meaning that this thing is not hermetic. That means that it's not completely insulating, meaning that it exchanges heat with its surrounding. Then in this case, the temperature is the same. Then if I change P and V, then the only thing I can do in this case, if I go back to this law, where did I write it here? I forgot even where I wrote it. I think I probably, yeah, in here. So when I change the, well, since these two numbers are fixed, R is fixed. R is a constant, doesn't change at all. So in this case, that's the choices I have between P and V, okay? Now, another case, I could have a process where the volume is kept constant. If the volume is kept constant, then I change the pressure by changing the temperature and vice versa. Now, if I keep the pressure constant, then I have two choices. The volume and the temperature will be proportional to one another, okay? So that's basically, R is constant. R never changes. R is the same everywhere. Why is this thing ringing? I'm sorry. Okay, again, this is P increasing by 3. So the volume, no, I'm sorry, the V is tripled. Then in this case, the pressure has to go by a factor of 1/3. Again, buoyancy is also true in the case of air. And we already gave an example of it when we talked about the balloon. Okay, so that is the same thing. And that's what I was talking about where you get in liftoff. And that is the same example when we were talking about the case of the fluids. So it's still the same thing. A dirigible that hovers in air displays its volume of air, displays its weight of air. Now it's hovering. So it's not rising, it's not coming down. So its weight also must have been equal to the weight of the displaced air. Okay? So both A and B are true. So that's the correct answer. Because it's hovering, it's not going up or down. Which brings me to another kind of principle that we didn't really talk too much about in the case of liquids, but it's true there too, and it's true for all fluids, which is Bernoulli's principle. Bernoulli's principle has to do with the pressure and has to do with how fast the liquids are moving or the fluids are moving. You see now, before, in the case of Archimedes and in the case also of the buoyant force and Pascal's principle and all of that, we're talking about fluids that really don't move, okay? Bernoulli's now equation actually deals with the fluids in motion and actually steady motion more so than anything else, okay? So if you take a hose, for example, okay? And I'm waiting for the hose to show up. And let's say, for example, this is the opening of the hose. And you turn on the water, okay? The water probably will come out with a certain flow, steady flow. It's going to come out in here and it's going to follow a projectile motion, which we have seen already. There is no problem with that. But what happened to the water flow if you squeeze this end, for example, of the fluid? You're not going to change the water flow from the other end. From the faucet, you left it the way you turned it on earlier. So that's no problem. That did not change at all. So all you did now is squeeze the end of the tube now. You will notice immediately that the projectile motion will have a higher range, meaning that the fluid will come out with a higher velocity already. That is Bernoulli's principle in action for you, okay? In other words, and that actually has to do with the conservation of matter to begin with. In other words, the area in here matter, okay? The area in here matter. So, what I'm thinking in here, I have a streamline of fluid that is coming up. Now they want to squeeze themselves through a smaller, narrow area, and because it's coming at a constant speed, a constant flow, that means that the speed with which they need to emerge on a smaller area has to be greater in order to account for all the flow that has passed by this point and now needs to pass by the other point. So that is basically in a nutshell what it is. Bernoulli's equation really talks about, in actuality, there are three things, but we're going to talk about two things for it now. We're talking about the pressure, P, I'm waiting for it to appear, and the kinetic energy, or the square of the velocity. Square of the velocity is the kinetic energy, by the way. Okay. Oh man, cannot even draw plus. So the square of so I cannot really call it kinetic energy because actually this is an energy density. Okay. Because 1/2 of the density of the fluid times its square, the velocity square, that is actually the energy density. So this too must be constant. Plus, if in case the hose, for example, extends in the air and now has height, plus the density of the fluid times the force of gravity times the height. So this is gravitational energy. So what the principle of Bernoulli is actually conservation of energy. The pressure from one side and the pressure from the other side is actually the work from both ends of the tube. And the gravitational potential energy and the kinetic energy on one side is equal to the other one. How can you see it in practice? If you have seen a wing, for example, of a plane, and let me wait for this drawing to come up. You know what? Let me see if I can get another place in here because I really want you to understand this point in here. I'm going to stop sharing that screen because I want to really make this point in here using a different screen because for some reason PowerPoint is extremely slow right now. So here is, oops, I'm not drawing now. What happened? Is it Zoom that is causing this problem? No, it's working now. So this is more or less a wing of a plane, okay? The plane is taking off. It's trying to take off, at least. It's going on the runway. It's going faster and faster, moving in the runway. I can think of the plane in the following fashion, that the plane is actually stationary, not moving at all. But what happened in this case is the air is rushing to the plane. So if somebody is sitting in the plane, he thinks that he's sitting stationary because he's drinking his water. He's drinking his cup of coffee, for example. So as far as he's concerned, if the plane is going at steady speed, moving with a constant speed, he cannot tell. He thinks that the entire air surrounding the plane is actually coming to rush to meet them. As a matter of fact, even the road underneath, or the tarmac, or whatever that thing is called. So that is, the whole thing is coming, rushing toward them. So in particular, the following things are coming to them. Let's say, for example, the air is coming this way. Okay, so this is a particle of air that was way far away from the plane. Okay, I tracked it until the plane passes by it. Now here is what it is. Okay, okay, this is a calm air, and this is also calm. And as the plane is rushing through this one, it's creating a problem in between it. But as far as the air is concerned in here, it's calm before the plane, and after the plane leaves it, it's calm. So the state of this air, which is the same, by the way, this and that are the same. So as the plane moves around it, the air is the same in that point. Do you understand that? So the air was calm. After the plane passes it, it's going to come back to its state, calm again. So this particle of air that was sitting in here now has to go around, up, and come down and be here now. Okay, this particle of air number 3 has to go this way under the wing of the plane and meet its friend in here. Okay, so the state of the air is the same everywhere before the plane rushed through it and after the plane rushed through it. For that to happen, this stream must travel faster than this one if they will to meet at the same time again. So they say their goodbyes before the wing passes by. They're split up and they have to join again for the state of the air to stay the same. So this must travel faster. So the velocity in here is higher than this velocity, which is lower. Okay? And because the velocity squared plus the pressure plus some number in here that I didn't write, which is the density of the air, which is the same for both of them, okay? And this is the pressure below, and this is the pressure above, okay? This is the velocity of the streamline above, and the velocity of the streamline below, okay? Because this velocity is higher, and this velocity is less, to make up for the difference so that Bernoulli's equation works perfectly, this pressure must be lower than this pressure. So the pressure below is higher than the pressure above. So this pressure must be higher than this pressure. And that's how planes take off. Because that difference in pressure on the wings creates a lift, an initial lift. Obviously, when the plane now is airborne, the pilot will move the wings a little bit, adjust them to gain more lift, okay? But that's another thing. The thing with it is he did not have to do that, or she did not have to do that while the plane is trying to gain speed. Once it reaches a speed high enough, this difference in pressure, the lift, will be high enough to overcome the weight of the plane with everybody on it and all the luggage and everything else, okay? And lift the plane from the ground, and the plane takes off. So that is Bernoulli's principle at work for you. Of course, somebody discovered that you can take this wing and put it backward, okay? Take the wing and put it like this, okay? Now, if you do that, the same principle works. The pressure on this side will be less than the pressure on this side. Okay? Exactly, Kyle. So Kyle is saying that this is actually what NASCAR cars do. They put the wings backward. And you know why? Because they want the car not to be airborne. Because they have so much speed so that it stays on the track and gain more traction so that they can gain more and more speed. So they have to reverse the structure of the wing to have more pressure using Bernoulli's principle again, because the air rushing underneath in here must travel faster than the air above the wing in here, and that creates for you actually a force to push the car on the ground. Otherwise, you will see NASCAR cars, all of them flying. So basically, you need to reverse the wing backward to make it work that way, okay? So that's the same Bernoulli's principle. Somebody else thought about this one very hard, apparently, and they actually take this class a lot, okay? Namely, somebody is throwing a baseball, okay? And he gives it an English spin, one way or the other, up and down, doesn't matter. For me right now, what I'm trying to think of is a ball that is spinning this way, okay? And it's moving in this direction as it's moving. Obviously, if I am a tiny creature living on the surface of this planet baseball, okay, here, I see the air is coming and rushing towards me. I don't know if the ball is moving. I live there. I mean, as far as I'm concerned, there is no problem with this. So the air is coming, rushing this way, in the opposite direction, here, with the speed of the ball. In addition to that, on the top, I feel this motion on this way. So as far as concerned, everything is actually moving in the opposite direction too, okay? And in here, I'm moving this way, and the air is moving. I'm sorry, I have it backward. So the last point is not correct. So if I'm moving this way, this is my actually speed on the surface of the ball. On this side now, it's still the ball is moving in that way, but now I am drifting in the same direction. Okay, there is a higher velocity now on this one, so that means that there is less pressure now than the higher pressure in here, okay? And this is the so-called sinker in baseball, okay? And there are all kinds of curved balls, basically, that pitchers can throw. So there's all kinds of applications for it. Another one, for example, is the atomizer, the one that is used, for example, for perfume. So all kinds of things, applications for this one. Another application, for example, in the early days of aviation, it was used to measure difference in pressures and how fast actually it's used to, how fast the plane is moving. So it uses the difference in pressure because as the plane is moving, it's going to create the air that is rushing through it is going to create a difference, and that is a gauge the pilot would look at and see how fast the plane is moving using the same principle. So again, you go back into the slides. This is Bernoulli's pressure for you. There are all kinds of applications. If we were in class, would create a vacuum under two pieces of paper, and then I would ask you, all of you, what would happen to the paper, which way it's going to bend. Some of you probably think since I'm blowing underneath, it's going to bend upward. Actually, it's going to bend downward because, again, I'm creating a lift. I mean, actually, an inverse lift in this case, so it's going to sink, okay? Again, I talked about this one in here when I was talking about principle, and this is the laminar flow versus the turbulent flow. If the velocity of the fluid becomes too high, then we have turbulence. Case in point, for example, tornadoes and other motions that are not linear anymore, but they are chaotic, non-linear. Okay, I think we're 5 p.m. And all of these questions are related to it. And when two trucks are passing one another, again, if they are passing on one another, there is a relative motion here, and the air between them is coming at a higher speed, and they could actually come closer to one another if that's the case, because the fluid between them, there is a difference pressure from the other sides that push them toward one another. Okay. Brings me to the final state of matter, and I think we talked about this one, which is an ionized version of a gas. Usually it's hydrogen, okay? That's at least how it exists in nature. And in the case of applications, yes, you can have the flames, which is ionizations and all of that. This is the main form of matter that exists in the universe. Think of all the stars. Think of the sun, which is 99% of the solar system. It's plasma state. So most matter is actually in the plasma state because of the fact that it is made out of stars. That's how they are made up of. And if the solar system is an indication, most of the matter is in that state. Not in the gas state, not in the liquid state, not in the solid state. It's in the plasma state. One of its applications is, for example, lighting, of course, all of it has to do with that. And one of its applications is a TV and the different pixels that form, again, because of the excitations and the different colors that form because of that. So again, I don't think that we're going to spend too much time on plasma state. And this is in a nutshell, chapters 12 through 14. So on Thursday, when we meet, we're going to introduce a new topic, namely thermodynamics. And of course, don't forget that you have the exam for you guys. And the discussion point is on Bernoulli's equation, and try to find other explanations, or at least explain the principle of the wing, okay? How does the wing work? Okay? Whether in a race car or how does the wing work to create either liftoff lift or traction. I forgot the question mark. Good. Okay, I see you guys Thursday. Meanwhile, I'm not actually done with your lab for Physics 11. Hopefully, I will finish it tonight. And I will publish it tomorrow morning. See you guys. Bye.